In this video, we focus on a group of molecules referred to as amino acids. These are going to be molecules that have both an amine group and a carboxylic acid group and are fundamentally important because they represent the building blocks of proteins. Here in this video, we will focus on some general features that are common amongst all of the amino acids. In the next video, we'll take a closer look at some of the individual amino acids and evaluate some of their physical and chemical properties. Here we see the standard skeleton that is common amongst the 20 standard amino acids. Those 20 standard amino acids are the building blocks of typical proteins. You will notice in this common structure that we have at one end of the molecule a carboxylic acid group. We refer to this as a carboxy group. At the other end of the molecule, we have an amine group shown here. And then in between the two groups, we have a carbon atom here in the middle between the carbonyl carbon and the amine nitrogen. And this carbon is referred to as the alpha position. I'm going to go ahead and label that with the symbol alpha there to represent that. And it's alpha relative to the carbonyl group, where the carbonyl group is the starting point. The first atom away from that we would call the alpha position, second position away from that would be the beta position, and so on. It's here at the alpha position where we have a so-called R group, and the R group is the variable group between the different amino acids. So R is going to be equal to a variety of different groups. Some of those groups will be acidic, some will be basic, some will be polar, some will be nonpolar, some will be aliphatic, some will be aromatic. You get the idea. And it's going to be these R groups that give the structural diversity to the individual amino acids, and then individual amino acids will link together to form proteins, and it's going to be the identity of these individual amino acids that lead to the diverse array of protein structures and functions that we observe. So it's ultimately going to be the R groups that allow us to distinguish between different amino acids. When we are drawing and recognizing an amino acid, we will always see this carboxy group, we will always have an amine group, and then this carbon here in between the two will be where we have our variable group. As we look at the 20 standard amino acids that are the building blocks of most common proteins, what we find is that those 20 standard amino acids all have stereochemistry in common. 19 of the 20 standard amino acids have a chiral center at this alpha carbon position, where I'm putting a star here. This is generally a chiral carbon because, except in the case of one amino acid where the R group is equal to hydrogen, in every other case, this group, this R group, is different from the other three groups that are bonded to that alpha carbon. Remember that a chiral carbon means a carbon that has four different groups bonded to it. So hence, when this carbon is bonded to the carboxy group, bonded to the amine group, and bonded to the hydrogen, as is required for it to be an amino acid, and then this R group is any other group other than those three groups that are already bonded there, this is going to make the alpha carbon a chiral carbon. So if the R group, for example, is a methyl group, then that would mean there's four different groups bonded here at the alpha carbon, and that is a chiral carbon. In all of the cases where the chiral carbon exists, the chirality of the molecule is going to be L. In other words, we would say that the molecules have an L configuration. What that means is that if we placed this particular amino acid into plain polarized light, it would rotate light to the left, and that implies the stereochemistry of the molecule. On the other hand, the enantiomer, the mirror image of this amino acid, would rotate light to the right. We would call that the D configuration. And so, with the 20 standard amino acids, when they are present naturally in proteins, we're going to see that the stereochemistry is the same across those different amino acids, where the natural form is all L amino acids. And this has to do with the way that these molecules are synthesized biologically, that when the molecules are synthesized within living things, the synthesis reactions that prepare those molecules install the L configuration. They install that special shape to the molecule, and that shape is essential to the biological function of these molecules. So taking a close look at these amino acids, the structure that I just drew for you on the previous panel was aligned like this, where we have, again, our alpha carbon bonded to our R group. This represents our chiral carbon. Here's that alpha carbon. And then we have at one end the carboxy group, and at the other end we have our amine group. And remember from our previous discussions in earlier videos of carboxylic acid groups that carboxylic acid groups are relatively acidic, meaning that they easily lose a proton relative to other organic molecules. And that's why they're referred to as acids. So they easily lose H+. Specifically, the proton that they lose is this one that I'm highlighting here in pink. And when they lose that proton, this oxygen becomes an oxygen anion. On the other hand, amine groups over here, where we would have a lone pair on the nitrogen if we were drawing out that as a Lewis structure, this group is basic. And being a basic group, that means that it easily gains a proton. And so within this molecule, we have at the left-hand end of the structures I've drawn here, a nitrogen that can easily pick up a proton to become NH3+. And at the right end of the molecule, we have our carboxy group that is acidic and can readily lose that hydrogen that's shown in red. And so what happens in physiological pH conditions, in other words, at a pH of 7, neither acidic nor basic, at a pH of 7, that's the typical condition within the body, what happens is that this amine group isn't found as just a neutral NH2, but instead at physiological pH of pH 7, the preferred state of that molecule has that extra proton. In other words, this base has reacted with a proton from an acid to become the so-called conjugate acid. So it becomes NH3 with a positive charge on the nitrogen. On the other hand, at physiological pH of pH 7, the prevalent form of COH isn't COH, but instead it is COO-. Because at that particular pH of a pH of 7, the conditions are such that it's most favorable for this proton, OH, to be lost and to become the oxygen anion there. We have a special name that we refer to a structure like this where we have one end with a positive charge, the other with a negative charge, and that term that you should be familiar with is the term zwitterion. Zwitterion refers to a molecule that has both positive and negative formal charges present within the same structure. And this is typical of these 20 standard amino acids, is that at physiological pH, they are generally found with the nitrogen atom positively charged, having picked up an extra proton to form an ammonium cation. On the other hand, the oxygen is negatively charged, having lost a proton from the carboxylic acid group. And so be aware when you see the structures of amino acids, you may see them either drawn as the zwitterion form, which is most biologically relevant to be honest, or you may see them drawn this way, with the COH and the NH2 groups intact and no formal charges. We refer only to the top one here as a zwitterion because zwitterion has the very specific definition that it has to be something that has a positive and a negative charge within the same exact structure. Now we're ready to continue into the next video where we take a closer look at the 20 specific amino acids and start to unpack some of the key terminology that goes with those and some of the key descriptors that we can use to evaluate each and some of their specific properties and uses.